Imagine discovering a black hole so enormous that it challenges our ideas of what's possible. This is exactly what makes the recent measurement of a supermassive black hole, weighing in at 36 billion solar masses, a groundbreaking revelation. But here's where it gets controversial. Is there a limit to how massive these cosmic giants can get? Or are we just at the beginning of understanding truly colossal black holes? And could such over-the-top massiveness hint at a different story about how galaxies and black holes evolve together? To unravel this mystery, let's start with what we know about black holes lurking at the centers of galaxies. Our own Milky Way hosts Sagittarius A star, a black hole tipping the scales at around 4 million solar masses. Massive, but relatively modest, compared to its more gargantuan counterparts in larger galaxies. For example, the Andromeda Galaxy's central black hole exceeds 100 million solar masses, while the giant elliptical galaxy Messier 87 features a black hole that's been measured at approximately 6.5 billion solar masses. In the universe's more massive galaxies, supermassive black holes often hover around or above 1 billion solar masses, making such enormous objects a common sight among the universe's giants. However, even in these monstrous galaxies, the black hole's mass is typically just a tiny fraction, about 0.1% of the galaxy's total stellar mass. This ratio, approximately 1,000 to 1, with stars outweighing the black hole, is consistently observed across many nearby galaxies. But pinning down the exact mass of the black hole isn't always straightforward. Usually, it requires detailed observations of stellar motions close to the galactic center, which is feasible only for galaxies within roughly 1 billion light-years due to the resolution limits of our telescopes. Now, thanks to the amazing tool of gravitational lensing, astronomers recently achieved a remarkable feat. They measured the mass of a black hole at the heart of the so-called cosmic horseshoe, a distant galaxy about 5 billion light-years away, despite its vast distance. This lensing effect, a natural magnification created by a massive 4-gram galaxy bending the light, allowed scientists to precisely estimate this black hole's weight at a staggering 36 billion solar masses. What's striking is that this black hole seems overmassive relative to what we'd expect for the galaxy's properties, raising new questions about how these massive objects form, more questions than answers, in fact, and feeding into the ongoing debate about the chicken or egg problem of galaxy and black hole development. At the core of nearly every galaxy, stars orbit in a complex dance influenced significantly by the supermassive black hole. If a star ventures too close, particularly in systems with multiple stars, it might receive a powerful gravitational kick, ejecting it from the galaxy entirely. While all galaxies are embedded within extensive dark matter halos, there is ongoing speculation that some low-mass galaxies previously thought to lack supermassive black holes might actually harbor hidden ones. Let's revisit that classic question we often hear as children. Which came first, the chicken or the egg? In evolutionary biology, the egg predates chickens by hundreds of millions of years. But when talking about galaxies, the question transforms into, did the stars in a galaxy form first, or did the supermassive black hole arrive before or alongside the birth of the stars? Here's where it gets tricky. One scenario suggests gas clouds collapse to form stars first. Some of those stars then end their lives as supernova, leaving behind black holes that grow over time. These black holes could merge and accumulate material, eventually forming the supermassive ones we see today. Alternatively, the black hole seeds, fewer and larger, could originate first, forming through exotic processes like the direct collapse of dense gas clouds in the early universe, or through primordial black holes created just moments after the Big Bang. Over billions of years, stars would then form around these seed black holes, which would grow rapidly through accretion and mergers. Distinguishing these scenarios hinges on observing galaxies across cosmic time. If black holes generally form after stars, Early galaxies should show black holes proportionally smaller relative to their stellar mass. But if black holes often arrive first or grow too rapidly, we would see more overmassive black holes in the universe's infancy. To test this, astronomers study galaxies at different distances. For the farthest ones, direct measurements of stellar motions or event horizon imaging become nearly impossible due to resolution limits. Instead, they rely on indirect estimates, such as analyzing X-ray signals emitted near the black hole, or the velocities of stars inferred via spectral observations. A graph plotting black hole mass versus central stellar velocity dispersion reveals a tight correlation in nearby galaxies. Most points align on a If these overmassive black holes are common in the early universe, it suggests a scenario where black holes frequently formed from massive seeds, tens of thousands of solar masses, rather than just from the growth of stellar remnants. This supports a hypothesis that black holes may have predated the bulk of galaxy stars. Essentially, black holes arrived first. That would turn the traditional stars first, black holes later paradigm on its head. Looking ahead, the detection of such huge black holes in distant galaxies has profound implications. It hints that the universe might be more efficient at forming massive black hole seeds than previously thought. As future telescopes, like the Vera Rubin Observatory, continue to scan the skies, we expect to find more gravitational lenses and galaxies hosting these cosmic giants, more pieces to the grand puzzle of the universe's evolution. Could we soon witness more black holes breaking the supposed upper limits of mass? And if so, will that force us to rewrite the rules of cosmic growth? All things considered, the discovery of this supermassive black hole at 36 billion solar masses is more than just a new record. It's a potent clue that challenges our understanding of the universe's origins. Are black holes the cosmic architects, or did they merely follow in the footsteps of star formation? The answer might just reshape our entire view of cosmic history. What do you think? The universe's biggest black holes tell us that black holes came first? Or is there still room for the traditional story? Drop your thoughts below and join this cosmic debate.